Okay. Good morning, everyone, and welcome to today's seminar here in the conference room of Rome, and also for those connected in streaming. This is the final seminar organized by Annals Geophysics journal for celebrating the 25th anniversary of INGV. And we are delighted to have as our guest Professor Kyle Rollins. Thank you for participating to our celebration. None of this would have been possible without the support and the commitment of many colleagues. And I would like to thank in particular the technical staff whose expertise resolved numerous problems that we had in along this period and during these seminars. Special thanks also are due to the coordinator 25th anniversary, Pier Giorgio Scarlato, for his support provided in various ways during this period. And now a short biography will be presented by Sara Moroso from University of Chieti, and then the discussion at the end of seminars. So enjoy the talk, and please, Sara, could you introduce Professor? Thank you.
Good morning to everybody, and thanks to be here. We have the honor to have Professor Kyle Rollins from Brigham Young University that will give a talk on developing a liquefaction prediction equation for gravel based on DPT block count and shear wave velocity at field case history sites. Thanks also for the people that is connected in streaming, and I would like to tell them that if they have any question, they can do at the end of the presentation, filling out the form that is available online on the YouTube channel. So I will give you a short biography of Professor Kyle Rollins, who received his bachelor degree from Brigham Young University, BYU, and his PhD from University of California at Berkeley with Harry Seed. After working as a geotechnical consultant, he joined the civil engineering faculty at BYU in 1987, following his father, who was previously a geotechnical professor. His research has involved deep foundation behavior, geotechnical earthquake engineering, soil improvement technique, and gravel liquefaction, bridge abutment resistance, and collapsible soils. He pioneered the use of blast-induced liquefaction testing to evaluate ground improvement effectiveness and pile performance in full-scale field tests. Over the past 10 years, he has worked with colleagues from around the world to investigate gravel liquefaction sites and develop a liquefaction triggering curve for gravelly soils. The American Society of Civil Engineers, ISCE, has recognized his work as the Huber Research Award, the Wellington Prize, the Rollins Hayward Baker Award, and the Henry Bolton Seed Medal. He was cross-Canada geotechnical lecturer for the Canadian Geotechnical Society in 2009 and cross-USA lecturer for the ISCE Geo Institute in 2023-24. Since 2013, Professor Rollins began a close collaboration with INGV, performing research on liquefaction with the execution of in-situ geotechnical and geophysical surveys and blast tests in Italy, Croatia, New Zealand, North and South America. Of particular interest to Italy, Professor Rollins led the performance of 3 liquefaction-induced blast tests for studying the natural and treated silty sands in the liquefied area of the 2012 Emilia seismic sequence. These are the first and only full-scale experiments carried out in Italy to reproduce and monitor the liquefaction phenomenon. These tests also evaluated the liquefaction-induced downdrag and soil improvement. Moreover, he guided research of gravel liquefaction using dynamic penetration test and shear wave velocity measurement in the epicentral area of the 1976 Friuli and 2009 L'Aquila earthquakes. Finally, he supported in-depth study to evaluate the influence of superficial crust on liquefaction-induced settlement in Emilia-Romagna using piezocone and seismic dilatometer test. So Kyle, is your time.
It's a pleasure to be with you in Italy this morning, and thank you so much for coming. I know your time is very valuable, so I appreciate you taking the time to listen to this presentation this morning. This is a photograph of my campus at Brigham Young University. Those mountains were right up against the Rocky Mountains, and these are produced by normal faulting. And about 80% of our population lives within 20 kilometers of the fault line. So earthquakes are a big concern for us here. We have about 35,000 students at Brigham Young, and that makes us one of the largest private universities in the United States, and it's sponsored by the Church of Jesus Christ of Latter-day Saints. So some of you may not know where Utah is. You probably know where California is in the United States, and we're a couple states in. This is Brigham Young University. It's located in Utah, where we had the 2002 Olympics. I know you had Olympics here in Torino. And we're also selected for the Olympics in 2034. So I think that's the first time they've had this in the same place. There are 5 national parks in Utah, spectacular geologic scenery, large cliffs, unusual erosion features in Bryce Canyon. So it's a great place for a geologist to visit. So we hope you'll come sometime if you haven't already been there. We're about 9,300 kilometers away from Rome and INGV, so you might think, that's quite a long ways away to have the potential for collaboration, right? But if you have the right perspective, you'll realize that we're just next door neighbors, right? We're very close to each other. And the world's becoming smaller and smaller every year, so we have the opportunity to collaborate online very easily now, and we can travel back and forth quickly. So as a result of that, we've had some good collaborations with partners in Europe. So I also saw there's some similarities between things in Utah and things in Italy. In Italy, you have narrow canals between tall buildings. Okay. And in Utah, we have narrow rivers between tall rock cliffs. In Zion's Canyon, for example. In Venice, you might have these narrow passageways where you can easily get lost if you're not careful, right? And in Utah, we have slot canyons where if you're not careful, you'll end up who knows where. You can get trapped in those pretty quickly, or big storms. So there's some similarities. So we're going to talk about today about developing liquefaction prediction equations for gravels. And it's going to be based on a couple institute tests, the dynamic penetration test and the shear wave velocity. And these are all from field case histories throughout the world. So our research sponsors are the U.S. Geological Survey, the U.S. Bureau of Reclamation, the National Science Foundation, and the U.S. Army Corps of Engineers, who has responsibility for large dams. So we are really grateful for this support that makes all this work possible. We're also thankful for our collaborators that we've had here, and I've just shown several of them. Hope I've got all the names put together right, but we're so happy that we had this opportunity. When I got into academics, I thought I'd be writing papers and teaching students, but I didn't realize that I was going to have friends here in Italy that I appreciate so much, and friends in different places around the world. So thank all of you for helping us to do this work. And also other friends, Paula, Maria, and Diego, who've stepped in to help us do work that we needed to get done when it was really critical for them to help. So thank you all. We're going to talk a little bit about the background of gravel liquefaction and in situ tests. We'll talk about how we collected gravel liquefaction case histories. We'll talk about the new DPT and V sub S triggering curves. Then we'll see, do these make any sense? So we're comparing them against different in situ tests like the Becker penetrometer test and comparisons with the CPT at sites at the Wellington Port in New Zealand where this testing was done. So when we think about liquefaction, we think about bearing capacity failures, cause damage to buildings like in Turkey, damage to ports from lateral spreading like this in Kobe, Japan, damage to deep foundations like these in Niigata, Japan, where these, let's see, right there, where this was the liquefied soil boundary, and damage to bridges like this one in Costa Rica that we investigated, where the bridge was pushed right off into the river from the lateral spreading. If we look at the soils that typically liquefy, this is the gradations that we normally see. But you ask yourselves, this is all sand. Can gravels really liquefy? Can gravels really liquefy? Professor Seed did some numerical studies early on, back in 1976, and found that if the permeability of the soil, or the hydraulic conductivity, is greater than 0.004 meters per second, the pore water pressure would dissipate as fast as it could be generated in an earthquake. So this gave everybody some relief. Well, then that's probably not a problem for us. All right. But I'm here to tell you that there's a danger from loose gravels. This is a highway sign in Alaska. But it's not just from loose gravels that you might slip on, or your car might slide on a pavement. It's from earthquakes. So there are now over 25 earthquakes where case histories have been reported that gravels have actually liquefied. And so we have to be concerned about this. We can't just say, oh, this happened somewhere, but it won't happen here. So there's several in Italy, couples for sure, the Messina earthquake and the Friuli earthquake, where gravels have been, case histories have been reported. So we have to be concerned about that. So here's a plot of some of the gravel liquefaction sites throughout the world. It ranges from Alaska to Chile, Japan to United States. So across the globe, earthquakes are producing gravel liquefaction. If we look at the grain size distribution that we see here, you'll see that there's quite a wide range of gravel soils that have liquefied. And even though 50% of the soils are gravel, it turns out that the sand content is typically 30% or more. So the sand is playing a significant role. And fines contents might range from 0 to 20%. So the sands and the fines lower the overall permeability so that it can be liquefiable. So we're really not talking about clean sands like this that would be less liquefiable. We're more talking about sandy gravel, where the sand occupies a significant space. There's been some research that examined this phenomenon of sand-gravel mixtures. This is the boundary. Above that boundary, there shouldn't be any liquefaction. And if you have just a clean gravel with no sand in it, it's unlikely that it would liquefy. But research by Shea et al. Says that as the sand content increases and you get to maybe 30%, the sand fills up the void space between the gravel particles and lowers the permeability by maybe 2 orders of magnitude. And if it's medium sand, it's even lower. And if it's fine sand, lower still. Okay, so we don't have all the data for the permeability of the gravels throughout this case history, but we can use this equation to make an estimate of the hydraulic conductivity. And if we plot all the data points, that's where they all lie. So almost everything that we know of is below that boundary. Now there's also the no liquefaction case histories. They also plot below this boundary, but they didn't liquefy because the earthquake shaking was not strong enough to cause it to liquefy for the density of that sand. Of course, there could also be cases where there's some layer like this clay soil above here in the Chengdu Plain in China that prevents the water from draining out of the underlying gravelly soils. Okay? Or it could be a concrete slab here at a port facility. So there's really two kinds of materials that could be liquefiable. It could just be a sandy gravel with a low enough permeability that it can liquefy, or it could have some layer that is impeding the drainage, preventing it from draining during the earthquake shaking. All right. So here's some case histories that have occurred around the world, like the Friuli earthquake, where there's 80 centimeters of settlement underneath a building. So we also have damage to ports in Argostoli, Greece, in Kefalonia. This is at Manta, Ecuador, where these piles were damaged. Can you see the shearing and tensile failure here at these piles? We'll look at that a little more in detail. And this damage to these bridge abutments in Seward, Alaska, where they were pushed towards the river a meter or more. So the big concern about this is with port facilities and older dams. So the dams may have been built before the hazard was recognized, and there's this potential for a failure surface to develop through the liquefied soils. And many port facilities throughout the world have been created by loose rock or gravel that's been dumped in place. So we have ports in Greece, New Zealand, Chile, and Ecuador that have all experienced liquefaction. And trying to decide what to do about these dams and port facilities is multi-euro, million-euro decision. So it becomes very critical to figure things out. I first got involved with liquefaction of gravel when I was a graduate student at Berkeley in California, working with Professor Seed. The Egyptians had an alliance with the Soviet Union, and the Soviet engineers had designed Aswan High Dam and built it for the Egyptians, and then they had some problems. The Egyptians kicked the Russians out of the country, and then as the reservoir started filling up behind Aswan Dam, the weight of the water induced earthquakes that the Soviets hadn't counted on. And so it became a concern to figure out if this dam would survive an earthquake. They couldn't go back to the Soviets, so they asked the United States government to help. And Harry Seed was a consultant. I was a graduate student with him. And he said to me, we're going to do all these analyses with a mainframe computer, and we want you to take this personal computer and show the Egyptians that they could do this themselves on their own computers. So I would start this computer program running at 5 o'clock in the evening, go home, and wake up in the morning, come back to the office, and it was like at 9 o'clock it would finish running. It would run all night long to do this with some of these pretty primitive personal computers. And this is the finite element mesh. The Russians had, this was gravel, and then these green sections were sluiced gravel. They had gravel that was filled in with sand. They thought this would make it stronger, but filling it in with sand made it more susceptible to liquefaction. So this was a problem. Everything's okay with Aswan High Dam, that they found out it was just going to be fine. So how do we evaluate these things, evaluate gravelly soil liquefaction? Well, the traditional way has been to take soil and test it in the laboratory, and this is my colleague Ada Athanasopoulos Zekos, who's a professor at Berkeley, and she has a device that's 37 centimeters in diameter. It's a direct simple shear device, and so she can cycle this to see if it's going to liquefy. What's the problem with that? Well, you have to build your own gravel, and maybe that works for a dam, but if it's natural soils, you never really know if you get the aging effects and the microstructure that is developed in a natural environment. So people have been using in situ tests, as you know, like the standard penetration test or the CPT test, right? The problem is that these start to be unreliable as the size of the particles increases relative to the diameter of the penetrometer. So if the D50 size of the soil is equal to the diameter of the cone, it might reach refusal, and if its D50 size needs to be greater than is greater than 0.3 times the diameter of the cone, then it will be affected. Okay. So what are the solutions? We're going to look at three of them. One would be a Becker penetrometer. It's a very large tube that's driven in the ground like a pile. The dynamic cone penetrometer that we're going to talk about, the DPT. In situ measurements of shear wave velocity, which I'm sure most of you are familiar with. So here's the Becker penetrometer. It's like bringing a pile driving hammer to your test site, and it drives steel pipe that's 168 millimeters in diameter, 6 feet segments. So you count the number of blows, N sub B, as it's driving this into the ground with a diesel hammer. So this is, you imagine, an expensive process to do this. And then once you've got this Becker blow count, you have to correct it for the energy effects. Then you can go up to this curve and estimate the corrected SPT blow count, N60. Once you've got that, you can come into your favorite liquefaction triggering curve for sand and get the value of the cyclic stress ratio that would cause liquefaction. Now, if you look at that, though, there's quite a bit of scatter in this correlation right here. So before you even start, you've got built-in uncertainty about how things are going to behave that makes you wonder about whether this is a good idea or not. The big advantage of the Becker is it's the largest penetrometer that we have, and the effective gravel size are minimized. And it provides penetration resistance at large strain, which is different than what we get from a shear wave velocity test at small strain. Some of the limitations of the Becker is that it's very high cost to get it to the site. Often limits it to major projects like nuclear power plants, large dams, big excavations, and things like this. There's uncertainty with this correlation. It's not, this is the biggest problem. It's not available anywhere outside of North America. So if you're trying to deal with it in Taiwan, good luck, right? You can't do that. And then there's a lot of controversy about how to account for friction along the sides of that 168 millimeter shaft that you're driving in. As a simpler alternative, we could use this dynamic cone penetrometer, the DPT. It can penetrate through loose to medium dense gravels. It's fast, simple, economical to perform, and so it could be used for any routine project that you might be involved with. But the biggest advantage, in my view, is that it's directly correlated with behavior in the field. So we're not trying to have some correlation to get back to what sand might do. So this is the Chinese version of this. It's 74 millimeters in diameter, tapers back to 60 centimeter rod to reduce friction. It's driven into the ground with a 120 kilogram weight dropped from a height of 1 meter. So this is about 2.5 times the energy of a SPT hammer, and it delivers about 90% of that energy. Okay. So if you look at the standard CPT versus the DPT, the DPT is 110% larger diameter than the standard cone. So it's less affected by the presence of large gravel particles. So if the DPT is 74 millimeters, we can deal with soils that have a D50 size less than 22 millimeters. So that puts it right here. And essentially all the field case histories that we have would be acceptable. Now there are cases where you have big boulders in dams, and it's not going to work for that, right? But for these typical liquefiable gravels, it works just fine. It's continuously driven into the ground. We count the number of blows for each 10 centimeters. Then we multiply that by 3 to get the equivalent value for 30 centimeters. It's corrected for overburden pressure using a standard correction. It's corrected for the hammer that is delivered relative to the Chinese hammer. Right now there's no consideration for fines content, although we suspect that would have some influence as well. This didn't translate very well. We've also got an equation for relative density that's shown right here. And so you can estimate the relative density for any purpose you might need. This is supposed to say the friction angle is equal to 27.2 plus 0.174 times the relative density. So you can estimate the friction angle for well-graded and poorly graded soil as well. Okay. And these are all based on the Chinese experience with this and developing this thing. Now the Chinese had these large areas of on the Chengdu Plain, and after the Wenchuan earthquake, large 7.9 earthquake in China in 2008, all these red dots, these are zones where the gravel's liquefied, and they're clustered in these channels here. So their standard approach was to use this DPT, and they could go below the water table, find the zone with the lowest blow count on average, usually use more than a meter, and that would be the zone that liquefied, right? So they saw in the sites that they would go to, most of the sites that looked like the ejecta that was coming up was sand. Maybe a few gravel particles, though, you're seeing here, right? This caused 20 centimeters of differential settlement, so the school had to be torn down and rebuilt. The lateral spreading reached a meter as the ground moved towards this channelized river. Right? So we're seeing all the same kinds of problems that we saw with liquefaction in sand. So here's my friend Zhenjiang Cao. He was using this DPT and collected a lot of information, and then he said, now what should I do with it? He contacted us at BYU and asked if he could come work with us for a year. So we were happy to have him come, and you can see the red dots are where it liquefied, the open dots are where it did not. And he did some analysis with logistic regression analysis and has the probability of liquefying. You can see some of these points, even at 50% probability, some of these points that didn't liquefy are predicted that they ought to liquefy. So there's some points that are out of place here with this data set. And it's only based on one earthquake, right? But here they have 19 sites that liquefied and 27 sites that did not liquefy. So in comparison to what Cao's curves look like to curves that we typically use for sand, you can see that there are a lot more data points in the database that Cao had or a lot fewer in comparison to the results from Boulanger and Idris. and the curves between 85% and 15% are much closer together. So we want to make our curves look more like this. Another approach you could use is just to use the shear wave velocity. We're good at measuring shear wave velocity now, and it's a fundamental property of soil, but it is measured at small strain. So it doesn't necessarily require a borehole, although you need to know if gravel is there. You can use MASW is what we call it. I think you call it MASFA or something like this, right? But the same thing. But there is some uncertainty with this interpretation, so you have to be aware of that. And it may not give you the same resolution. For the DPT, you can identify a layer like this, but for the shear wave velocity, it might be over a meter or a few meters. And then all the curves that were available are triggering curves for sand with shear wave velocity, and we're not sure if those would be appropriate for gravel. For example, here's Rob Kahan's curves for sand with 422 data points in comparison to the curves from Zhao's data in China. But here it looks like if you have a soil with a shear wave velocity greater than about 240 meters per second, it won't liquefy. But Zhao's data is saying it might take something like 270, 300 meters per second to prevent liquefaction. So what we wanted to do then is go out and collect as much data as we could. So we got a grant from the National Science Foundation and from the Bureau of Reclamation. We started testing. This is the closest site to us. So we tested 3 sites there, and we thought, oh, we're done. We still have money left over. So we didn't go on a Caribbean vacation somewhere. We decided, let's see what we can get done with this. And believe it or not, these are all the additional sites we're able to investigate with collaboration from our colleagues around the world, which to me is rather amazing. Right? So we first went to Seward, Alaska. There were 3 locations, bridge sites across the Resurrection River here where there was liquefaction taking place, and we knew it was gravelly soil. So this is causing lateral spreading. You can see the bridge piers are rotated a meter or more, some cases 2 meters, and that's the site we were going to do. So we went to this site, and the Alaska Department of Transportation said, we will drill all the holes for you for free. So we drilled holes to 15 meters, 8 holes to 15 meters in 2 days. So it was really rapid, right? We measured the energy that was being applied. We did different hammer energies to see how that would be affected, and we measured the shear wave velocity at these locations. So a lot of work very quickly. So let's see. So this is one of the gravel sites. Do you think you could get this cone penetrometer into this? This is, I don't know, there's 50 millimeters to 100 millimeters in diameter. Everybody looked at the site and said, okay, let's try it, but I don't think it's going to work. All right, we'll try. So here it goes. And this is an automatic hammer instead of the Chinese. So it took about 20 seconds to go 1.5 meters. Everyone was surprised as could be, right? And we said, well, let's keep going. We were able to drive at 14 meters and then decided to stop. But everyone was amazed that this could get through these materials. Next site, we contacted Sara Amoroso, and she said, yeah, I think we can help you do these tests. And we went to Avicinas and Bordano up in Friuli area. There were 6 gravel sites that liquefied, And a bonus, in one of these sites, it had liquefied in 3 separate earthquake events. So we get 3 for the price of 1. We did DPT and MASW testing. This is the photo courtesy of Dr. Sirovich. And this is an alluvial fan. And this material down here is the gravelly material, and this is more like the sandy soil. You can see the ejecta in this cornfield that has a lot of gravel particles in it. All right. So here's Maria's drill crew with the track-mounted rig. We instrumented this rod to measure the energy that was being provided, and this is, I think that's Maurizio and Giuliano in the background, doing the data acquisition for us. It's amazing that they would help us out so easily, but they are excellent at getting data and interpreting it. So this was a big plus for us. About this time we had an earthquake event in Ecuador, and I was on the team that went to investigate afterwards, and this was my assignment, was to look at this port at Manta. And most of the ejecta that you looked at was sand. We thought, oh, this is typical sand. We measured how much it settled and everything like that. Then we went home. Well, we did go underneath and we could see the damage to all these piers, or these piles. Can you see what's causing this to slide? There's a big lateral spread with displacements of 20 to 100 centimeters. We thought, well, that's another lateral spread from the sand liquefaction case. But when our partners in Ecuador looked at this, it turned out that it was sandy gravel. The sandy gravel was sliding towards the piles and causing them to rupture. Right? So we got together with Professor Javier Vera-Granau, and he said, oh, we can do that. We can go do all the work. So this is the gradation on a 3-sided gradation curve. It's 35 to 75% gravel. Wow, surprise. Here's Javier. And so they did 7 DPT soundings. There was a seismograph that recorded 0.6 G right next to the port. We did PDA. They did PDA measurements, and they did 7 shear wave velocity profiles, so they could identify, working together with Javier, we identified these zones of liquefaction in these gravelly soils. Okay. Now it's really tempting just to focus exclusively on the sites that liquefied. That's the most glamorous thing. Everybody wants to go where there's ejecta and do a test, right? But if you only focus on the liquefied soil locations, let's see, then every additional data point you get shifts the curve to the right and becomes very conservative. So you have to really get out and do some no liquefaction tests to constrain the curve on the right so it just doesn't keep going out that direction. So this is less exciting, but it really helps tell you where the curve really should be. So we went to Valdez, Alaska. Our friends in Alaska said, yeah, we'll help you again. So this is what the port looked like before the earthquake in 1964, and this is immediately after. So 30 million cubic meters of material just went, slid out into the Prince William Sound, and this city behind here, lateral spreading of 8 meters. 8 meters. All the utilities were completely destroyed. So they said, we don't want to, there's no way we can live here anymore. They moved the whole city to another side of the sound over here. So this is the new Valdez. Here is old Valdez. So we did tests at the site where they had liquefaction and this new location where there was no liquefaction. So here's the testing being done while the tide is coming in. It was coming right up here, got to about right here before we finished. Brave drillers. We thought they would be stuck in the underwater. They got out. So if we look at this, this was a liquefaction point, low blow count, 7.8, CSR of 0.75, some of the highest CSRs that are in any database. And this is a zone that did not liquefy. The critical layer is 21 blow counts. So if we plot those on the curve, these are obviously liquefiable sites, and that's what really happened. And these are the two sites where there was no liquefaction. These become really critical points because they constrain the curve from going too far to the right. Looks like we've overdone it here. Right. Then Atazekos and Demetrius said there was an earthquake team that went to Kefalonia, just on the island, Kefalonia Island, west of Greece, right here, you see. And the port had slid out, and can you see all the ejecta? It's got a lot of gravel in it, right? So they said, can we get enough money to go over there? And so I paid for the drilling equipment, and they came in and did the shear wave velocity. So we had accelerometers right close to the port. We could do DPT soundings, PDA measurements, and we did this in collaboration with Ada and Demetrius Zekos. If you have to go to a test site somewhere, this would be a good test site to go to. It's beautiful, right? Track-mounted, this is all we needed to have, is this little track-mounted rig. Measured the energy provided by the hammer, and then it went to Argostoli. This had 3 separate earthquake events. In 2 of them it liquefied, in 1 it did not. So we're getting 3 for the price of 1 there. And then Demetrius and his graduate student Jonathan Hubler did the MASW testing along the port. Here, Jonathan's now a professor at Villanova in Philadelphia. And lastly, we did testing at Centerport in Wellington, New Zealand. Misko Kubernovsky was working on this site. He had done 90 CPT tests. And I said, do you think we could get on the port? He said, I'll see if I can work it out. And he did, and got us permission to come. It's hard to get permission to come to a port because so much is happening. They don't want to be bothered. But this port had liquefaction in the Kaikoura earthquake, limited liquefaction in the Cook Strait, and no liquefaction in the Grasmere earthquake, right? So this was a great site to test. It had 60 to 70% gravelly material. Here we are testing at the port. You have to be very careful because these things, everything's in commotion. It's always moving around at the port. And if you're not careful, you'll get run over. The truck will run right over you. So we've got safety cones here. And I discovered something else. In Ireland, they say at the end of the rainbow is a pot of gold. Do you have this saying here? I don't know. But it turns out, no, it's not a pot of gold. It's a drill rig. A drill rig is at the end of the rainbow. So, so anyway, those are the sites where we collected, some of the sites where we collected data. And then we started processing the data. And we would find the layer with the lowest blow count or lowest shear wave velocity. We also look at sometimes the cyclic stress ratio would be higher, so we'd look at the layer with the highest shear wave CSR and lowest blow count, so that we could identify that as clearly the worst site in the worst depth interval. For each one of those sites, we would calculate the CSR using this standard equation that accounts for the magnitude and the depth. This gives you some of the characteristics. Most of the sites the majority are from China, but we have data from the US, New Zealand, Greece, Italy, and Ecuador. A variety of geologic environments. Most of the sites have are less than 15 meters in depth, which is typical of all the liquefaction case histories. And we have data from magnitude 9.2 to 5.3. Okay, so quite a spread in data. So what we did is a logistic regression to get the probability of liquefaction. So this is the equation that gives you the liquefaction resistance in terms of blow count, the probability that you might want to use, and the magnitude. So now instead of one earthquake or 46 case histories, we have 137, 7 countries, and 13 different earthquakes. So the 200% increase in the data, and all those solid data points are where it liquefied, and the open are where it did not. All right. So this was published in December 2021. These data points right down here from Argostoli and in the port in New Zealand are constraining the data to shift it upwards because they didn't liquefy. These points from Alaska are really critical here because they are constraining the shape of the curve at the top end. We need more data points here, so if you know of any, especially sites that were gravel that didn't liquefy, we'd like to hear about that because that would really be important for us. So here's the curves that Tsao originally had are shown with dashed lines. The new curves are shown with solid lines. And you can see that the curves have shifted upward at the low blow counts. We had to do that to match the data, even though our previous effort was going almost through the origin. And the 50% line, the blue lines, are fairly similar, which gives us some confidence we're not too far off. But the range between 85% and 15% is a lot smaller than it used to be. So we have more confidence about what we're doing. This makes us happier and engineers more likely to use this design process. We also did the same thing with the data we had for shear wave velocity. Once again, these are pretty tightly constrained. There's even more case histories because there's more people who have done shear wave velocity testing than have done DPT. So we have this from 17 earthquakes. Again, we have a pretty good fit here, even though we have a few points that don't work or on the wrong side of the curve. The uncertainty bands are narrower. So we need some more data for that. We found also that when you put more gravel into the mixture, the triggering curves relative to the sand curves here, they shift to the right. So it doesn't mean that gravels are more likely or less likely to liquefy, but it does mean that you have to have a higher shear wave velocity to say that there won't be any liquefaction. So you have to be careful about the gravel content and use curves that are based on gravel. We also back calculated magnitude scaling factors. This one's for V sub S and this one's for the DPT. And they fall right in the middle of what people are typically using for sand. This is for sand based on V sub S and sand based on SBT. So we think we're in the right place with those. They look about right. Since the shear wave velocity and DPT are trying to measure similar things, we thought like we could make a correlation. So this is the one we came up with, and most of the data points fall between plus and minus 25%. So if you don't have the money for a shear wave velocity or people that will do things for you almost for free, you can make a really crude estimate. Hopefully it's good enough for the purposes. Whenever you can measure it, it's always the best idea, of course. So let's look lastly at how this compares with other methods. We want to see if we're getting answers that are consistent with what we think is a correct analysis. So there's one set of sites in Idaho where the Becker penetrometer has been used, and we could go to those same sites and do the dynamic cone penetrometer test and compare those. So this just barely came out. It's not in print, but it's electronically available from the American Society of Civil Engineers Journal of Geotechnical Engineering. So this is the Boar Peak earthquake, the epicenter here. This is the fault line. And we went to Pence Ranch, Larder Ranch, and Whiskey Springs. So this is Ron Andrus. He and I did our master's degrees together at BYU, and he's a professor at Clemson University in the southeast of U.S. And these are slides from he and Les Youd. This is lateral spreading towards this direction. This fissure opened up 0.75 meters, and the sand and gravel came out of that. So we knew that was a gravel liquefaction site. So each of these sites where we had a Becker penetrometer, we did DPTs. So we have like 8 DPTs. This is Larder Ranch. Can you see this big graben here? This fault rupture, not fault rupture, the lateral spread, the scarp at the upper side is right there. So we did some DPT tests here as well. The lateral spread came down through here and came through the liquefied soil and then up at the river below. Then this is Whiskey Springs. Stokey and Andrus did tests here, did trenches to see where the failure surface was. It was going down through this dense gravel layer and sliding on this loose gravel layer here and coming out at the river back down here. Okay. So again, we had 3 BPTs, and we're going to do tests at 4 DPTs there. So here's a quick summary of all the data, the DPTs with the triggering curve at 30% and the BPT here. So let's go in and make a quick comparison. On average, what do we get? A factor of safety of 0.5 for the DPT for all the tests combined. And this is, with the BPT, a factor of safety of 0.4. So we're really pretty close to those two. You can look at them individually like this, but it turns out that we're doing quite well. So that was encouraging that we could get that kind of agreement between the 2 different methods. And this is the last one we'll talk about. This is the port of New Zealand, Center Port in Wellington. This was subjected to 3 earthquakes. All these brown areas are where gravel's ejected. So we're going to look at some of those sites. I don't expect you to look at this other than to get the equations, but this is all the equations that go into the CPT calculation. These are the equations that go into the DPT. They're 2 completely separate databases. They use different correlations, different correction factors. So we have no reason to expect that they ought to give us the same answer. This is a comparison of 6 of the sites. The orange curves are the cyclic resistance ratio, and this is versus depth, from the CPT. Sometimes it hits some gravel, and it reaches a higher value to get through the gravel particles. So you can see these spikes as you go down through the profile. So it's being affected by the presence of the gravel out there, right? And then sometimes it gets to a point where it reaches refusal and it can't go through. So they have to take the cone out, drill back down through this zone, and then start again. This was a couple meters, maybe 1.5 meters. And about 20% of the cases, they couldn't get through the gravel because of the high density or the gravel size. The blue curve is the curve from the DPT, and it's almost constant with depth through this gravel that was dumped in place. it's fill material. Okay? And as you look at these, there's really pretty good agreement between the CPT and the DPT at locations where the CPT can get through the gravel. The disadvantage of this DPT is it can't identify these layers that are shown as non-liquefiable, that are clay layers. So that's the weakness of the DPT. But overall, that's, to me, with completely different data sets for the triggering curve, different equations, that's the kind of agreement we can get, which is really pretty good. These are the sites that were predicted to liquefy by the DPT and did liquefy. Here's from the CPT. They're a little more erratic. These are the sites that did not liquefy. They're below our 15% curve. Most of them are below the 15% curve for the CPT. And these are marginal, so it's a little below the 50% probability, and these are scattered around. But when Kubernovsky and my students and I, we look at it, we think, yeah, that's pretty remarkable that we have this kind of good agreement between the CPT and DPT. So all these pieces of evidence make us feel a little more comfortable and lead to these conclusions that the new databases are providing a better constraint on the DPT and shear wave velocity triggering curves. They're based on multiple earthquakes, different geologies, and we think are reliable at this point. The V sub S value precluding liquefaction is higher when you have gravels in the mixture than if it's just sand. So people need to consider that when they're making predictions about gravel liquefaction. The DPT produced factors of safeties that are similar to those of the Becker penetration test, which is considered the gold standard in the United States, which is encouraging. And the DPT and the CPT-based triggering curves produce similar cyclic resistance ratios for loose sites at the Centerport in Wellington, New Zealand, confirming that this seems to be a reliable approach. I've put these references in. I don't know if you have a repository for these presentations. I know you have them videotaped, but if you need to access any of these papers, they're available there. And wanted to thank you for coming and hope you'll visit us in Utah and see the Delicate Arch is what it's called. It's about 80 meters tall. So come give me an excuse to go to these parks. Thanks a lot. Any questions? Yeah.
Yeah, thank you for the talk. Is it working? Yeah. I have two questions, and I haven't seen any correlation between the duration of the ground motion and liquefaction. I just curious if you do that, if you take that into account, and another characteristic of the ground motion, like if there is a resonance, is what's the frequency, what's the dominant frequency. I see there's the range of magnitude that can induce liquefaction are really big, so I don't have any problem to see that magnitude 9 produce a lot of damage everywhere, but if magnitude 5, is that a site that resonates and have an anomalous duration, or is that other thing? And then the other question, just how do you choose non-liquefiable sites to test? Just the presito gravel, is it enough, or do you need other characteristics?
Yeah, so this is one of the flaws of the triggering curves that are based on in situ tests, because we only assume the site liquefied if ejecta comes to the surface. But we know there could be cases where the soil liquefied in the ground, but for whatever reason, maybe it was too deep to come to the surface. It would be identified as a non-liquefiable site if nothing came to the surface. So this is a weakness of our methods currently. You have to have downhole pore pressure sensors to measure if there was liquefaction, or more recently, people are taking seismograms and looking for an increase in the period that indicates that the soil somewhere in the profile has liquefied. So that is being remedied by this approach. But that's right on the state of the art, I think, right now. See if I can go back without giving you motion sickness here. Sorry. Okay, right there. So what's typically done to account for the magnitude of the event, because what you say is correct, the larger the magnitude, the more likely it is to liquefy. And the way that's considered typically is to say that let's assume most of our data initially came from magnitude 7.5 earthquakes. So they had a scaling, developed a scaling factor. So if it's lower value, we scale down the accelerations by this, or the stresses by this scaling factor, right? And if it's a higher magnitude earthquake, we divide it by a scaling factor that's lower. So when we did the regression, the magnitude is a separate factor in the equation. So if it's a larger magnitude, that is accounted for directly. What you say about the peak acceleration is very true. And this has been a complaint that people have had for many years. It's a competition between how simple can we make the method but not be too simple. So peak acceleration seemed to be the best predictor, but still simple. Now others have used Arius intensity and other combinations of velocity, which requires processing and additional information, but they can get a little better prediction of the liquefaction potential by accounting for other frequency and other issues.
Arius intensity includes duration.
Duration, yeah. So, and there's other combinations of ground motion characteristics, but most people are staying with the simpler model, even with all this information.
Any other questions?
Sure.
If you plot separately the data points related to natural soils and man-made soils, do you notice any difference in the triggering curves or so?
This is a good thing. You would expect there to be a difference, right?
I don't
Typically,
know what to expect.
Yeah. Well, we have a lot more of the natural soils than we do the artificial soils, but the artificial soils are at that low end of the blow count range. To be honest with you, we haven't made the comparison directly, but it's a good idea, because you ought to think that there would be difference in resistance, right? Yeah, the natural that's had a chance to age should be stronger than the younger ones. We haven't done it, honestly. I think we probably have enough data that we could we can make that comparison. It's a weakness of our method at this point, right? We've lumped in a bunch of things like gravel contents might range from 25% to 75%, and that's a big lumping of data. My students right now are trying to look at these little variations like gravel content, fines content, sand content. Maybe I'll go back and tell Ali Wahlberger, you ought to look at what is the word for it? We have called it man-made fills, but anthropogenic materials. We could do that, and I'll have her look at that. Good idea. Hi.
Thank you for your interesting presentation. On the same line, also maybe splitting between different geological environments, because I saw in one of your slides that you have divided. I don't know if you already did or if you are have in mind to do, but maybe also it can be interesting to identify different material of different geological region.
Yeah.
My question was about your last point, if you go to the conclusion.
Yeah. Let's see if I can get back there. Oh.
VS value precluding liquefaction, that's one which is pretty strange, actually.
Oh.
What is the physical explanation, in your opinion, why a sand should, a gravel with sand should not liquefy with some VS, and the opposite, it should liquefy, and the sand with the lower VS not? I mean, do you have a physical explanation for this?
Yes, working hypothesis. It seems like the velocity moves faster through the gravel particles, and the gravel skeleton that's in there allows the soil to have a higher shear wave velocity. We've gone to we went to Maui in the Hawaiian Islands, and there we had coral gravels. They're weakly cemented. The blow counts were 5 and 6 from the SBT, so it clearly was loose material, liquefiable material. When we did the shear wave velocity, the velocity was higher than 230 meters per second. So we thought that what was happening is the developers were building high-rise luxury condominiums and saying that the shear wave velocity said it shouldn't liquefy. And the SBT said it was a real problem. But talking with Ken Stokey and others, we're thinking that that skeletal gravel allows the velocity to move faster than it would if it was the same density of sand in that same thickness. Does that make sense at all?
Yeah, great. Thank you.
I might also say that there's been a number of laboratory tests where they have mixtures of sand and gravel trying to maintain the same density, relative density or void ratio. And as the gravel content goes up, the shear wave velocity is also going up. And I'll share this with you as Ali's doing these regression analyses. We have for the gravel, when you try and account for the shear wave velocity and the gravel content in the field data set, you see that as the gravel content goes up, the shear wave velocity also goes up with the and the triggering curves are higher. Okay.